This is a video on exponential decay models. In our previous video we talked about exponential growth models. Exponential decay actually uses the same formula. Here we've got P of t equals P0 e to the kt, where k is less than 0. That's what makes it decay, is that our growth constant is negative. That's what the k less than 0 tells us. P0, remember, is your initial quantity or initial amount. And then P of t would be the amount at time t in the future. So, we use this oftentimes with radioactive isotope type examples, but you can see it in other ways, if a population was declining, things like that. So for this example here, we have strontium-90 has a decay rate of 2.8% per year, and they tell us the rate of change in the amount present, N, is given by this differential equation here. So, the change in N with respect to T is equal to negative 0.028 N. And what we learned in the last section was that things that have this form, this type of differential equation where it's just, the derivative is equal to a constant times the original function, all satisfy the same type of exponential equation. So in this case, because N is the name of our function, we're calling this N. We'll call it N of t, right? This is the change in N over the change in t, so the name of the function is N. And we have N of t is equal to, and if you remember, we said, usually we say this P0, but we're going to call this one, since it's N, we'll call it N sub 0, meaning the initial amount still. E to the, what's K? Well, K comes from our decay rate, but you also have it right here. This is K. The constant in front of N is the decay rate. See that negative sign in front? That means that the decay is what we have going on because it's negative, right? If it was positive, it would be a growth problem. So they say decay rate here, it's negative here. In our exponential function, we want to make sure you write the negative 0.028 for k, and then t will be for our time t. So that function satisfies the equation. They didn't tell us the initial amount, and that's okay, we don't need that. But we found the function we need. For part B here, so suppose 1,000 grams of strontium-90 was initially present. So they're telling us what we should think N0 should be. How much will remain after 70 years? So we're really looking for N of 70 because T is the time. So if I have N of 70, I'm just substituting in here. We know the initial amount they told us was 1,000 grams, so it's 1,000 e to the negative 0.028 times T is 70. And then we want to calculate this. If your calculator displays everything on the screen for you, you could just type this in as you see it. If it doesn't display everything on the screen, you want to make sure you multiply the exponents together first, then hit the E button, and then multiply by 1,000. So if we're taking a look here, we have 1,000 times e to the, now remember, this power is the entire power, so make sure you have the parentheses around the whole thing, negative 0.028 times 70, close those parentheses. And this gives us, we have 140.858. We'll round it to 2 decimal places. So we'll say this is equal to 140.86. And then what are the units on this? Well, this is the amount present after 70 years. So this is grams. And make sure you have the correct units there. You could just use G for grams if you wanted to. We know it's grams because the initial amount was in grams. So we started with 1,000, and it's gone down to 140.86 after 70 years. So that's an example where we actually use the exponential decay model, given that they told us what the differential equation was. For the next part, let's talk about this definition before we work on the examples. We have radioactive isotopes decay exponentially. So we know this about them. And then the blank of a radioactive substance is the amount of time it takes until half of the original amount remains. What we call this is the half-life. And you may have heard of this before, especially if you take in a chemistry class. So the half-life is the amount of time it takes until half of the original substance remains. Or you could, on the other hand, say until half of it decays. Those mean the same thing, right? So we're going to use the half-life to help us find the exponential functions that go along with specific radioactive isotopes. So in this next example here, it says the half-life of polonium-218 is 3 minutes. how much polonium-218 will remain after 20 minutes if 1,000 grams are initially present. So first off, let me point out polonium-218, that's the name of the radioactive isotope, right? It is not using the 218 in the problem. Just like in the problem above, we never actually used 90 in the problem. Strontium-90 was just the name of it. So the half-life of polonium-218 is 3 minutes. How much will remain after 20 minutes if 1,000 grams are initially present? So because we know that this is going to decay exponentially, I know I'm following, my P of t equals P sub 0 e to the kt power as the function. And now what I really want to do is come up with a general formula so then I can eventually sub 20 minutes in to see what I have. So we know the half-life. All right, and since you know the half-life, that's the first thing you want to use, because the half-life is actually giving us a specific point we know, and it gives us a way to determine what K is, right? What that growth or that decay rate is. So first, we're going to use our half-life to find K. Because once you have K, then you can write the general formula. So remember what the formula tells us. When we say half-life, right, we're talking about when half of the original amount remains. So even though they told us what the original amount would be, let's pretend like we didn't know. So the initial amount is called P sub 0. So if I wanted half of that, the amount that remains, instead of calling this side P of t, right, if there's half of it left, we'd say there's 1/2 P sub 0. Replacing this left side equals P0 e to the kt. Right, so half of the original amount remains is what we're looking for. And we're trying to solve this for K. Now we know the time. How long does it take for half of this to remain? Really, the time here, maybe I should put this parentheses right here, is 3 minutes. So we know that, right, the half-life is 3 minutes. And you need to use that here, right? So the half-life is 3 minutes. So at that time t, at 3 minutes, there's half of the original amount remain. You need both of those because we're trying to solve for K. So how do I solve this? Well, first thing you want to do is isolate the exponential. So we're going to divide both sides by P sub 0. When I do this, the P sub 0's cancel, and I'm left with 1/2 equals, here they cancel, e to the 3 times K power. And those cancel out. Sometimes people can notice this right away and they know you're just going to have 1/2 equals, because if this was one initial amount, right, 1 gram present or whatever you want to call it, there'd be only a half left. So those are always going to cancel in the same way. Similar to when we talked about doubling time in the previous examples. So once you're here, now I want to solve for K. I have to get it out of the exponent. The way we do that is by taking the natural log of each side. So we get the natural log of 1/2 is equal to the natural log of e to the 3k. Natural log of 1/2 I will leave as natural log of 1/2 for now. It's equal to, remember, natural log of e to a power. Remember, they have both base e, so log base e of e to a power is just going to be the exponent, so it's just equal to 3k. And then we'll divide both sides by 3, divide by 3. I end up with k is equal to, now it's natural log of 1/2 divided by 3. We want an approximation here. Because we're going to use it in the formula, this would be the exact value, natural log of 1/2 divided by 3. Let's approximate this to 4 decimal places. So make sure you take natural log of 1/2, it's natural log of 1 divided by 2. Make sure that's all inside of those parentheses, and then divide that by 3. If your calculator does not display the values on the screen, make sure what you do is you do the 1 divided by 2 first, then hit ln, then divide it by 3. So we've got this as approximately negative 0.2310. So K, this is an approximation. I'm using 4 decimal places, negative 0.2310. Now once you have K, all right, once you have K here, you need to use this in the formula, because we didn't answer the question yet, right? The question is how much will remain after 20 minutes if 1,000 grams are initially present. But this tells us that our formula is going to be P of t equals P sub 0 of e to the negative 0.2310 t. And because I didn't use anything here for P sub 0, I just kept it general, I was able to get to here. If I had called this the 1,000 they told us, I would have written 1/2 of 1,000 or 500 on this side, and you still would have ended up in the same place. Because I know I want to answer this question, now you're able to answer the question. So I will substitute in what I have here. So we're looking at P of what? We're looking at 20 minutes is T. So P of 20 equals P sub 0, which is now, they told us we're looking at 1,000, e to the negative 0.2310 times T, which is 20. And then we're going to calculate what that amount would be. All right, so we found K, so we could use our formula. And then once you have your formula, use the initial amount they told you, and then we can solve this. So if I clear this out, we got 1,000 times second e to the negative 0.2310 times 20 power. Make sure that's all inside the parentheses when you raise it to the power. And this is, we got 9.8527. So we're going to approximate this. I'll say to 2 decimal places, so we'll say 9.85. What are the units on this? Well, it's the amount that we have, right? How much do you have at 20 minutes? Well, if there are 1,000 grams present, there's 9.85 grams is what you want to use, because the units are going to be the same. So 9.85 grams are present after 20 minutes. Now, we did this by calculations. You can't show me work on this by just saying, okay, 1/2 of 1,000, that's 500, that's after 3 minutes. Then do another half and say, okay, it's another 3 minutes, and then add those all up. We want you to use these exponential functions to find this. And, when you're given the half-life, the first thing you want to do is use it to find K. And that's what we did here, because it gives you, at a specific point in time, whatever the half-life is, there's half of it left. So you could always find K like that first. Then we can use that to determine the amount that's left after a certain amount of time, or any amount of time T. Let's take a look at a couple more examples. If we have the half-life of carbon-14 is approximately 5,730 years. How old is an artifact that has lost, that word lost is important, so we underline it, that has lost 60% of its carbon-14? So when we're talking about this, let's make sure we know what we have to do, right? The first thing, since they've given us the half-life, is we're going to use the half-life to find K. We know that carbon-14 is a radioactive isotope, so we know we're using P of T equals P sub 0 e to the KT power. And we're going to use half-life to find K. Now when I do that, right, so I'm using the half-life to find K, the key thing here is they never even actually told me what P sub 0 is, right? It doesn't say anywhere in here the initial amount. And that's why we kind of did the last problem the way we did, is that I don't want you to get accustomed to always having it. Because if you don't, you still have to understand what half-life means. Half-life means that it's the amount of time it takes until half remains. So the half-life is 5,730 years. Then I know that half of the original amount, 1/2 P sub 0, is going to be equal to, well, P sub 0, the initial amount, e to the K times, now what's the time? We make sure you fill in for this. It's the time for your half-life, which is 5,730 years. All right, so you have this right here. We can divide both sides of this by P of 0 because you want to isolate the exponential so you can solve. And these cancel on each side. So you're left with 1/2 equals e to the, these cancel as well, e to the 5730 times K power. Now, if you know how half-life works, you're always going to end up in this scenario where it's 1/2 equals e to the whatever the K times T power is. And remember, time is what you're filling in for. We actually ended up with that same scenario here, right, when we did the problem in the last example. So if you can see that happening, you could right away type this in or write this down. That's okay. You can show me that that's how you would find the half-life, because it's really almost like making the assumption for one initial amount, there's half of it left. So if P0 is 1, this would be 1/2 on this side. Once you're here, right, we want to take the natural log of each side to solve for K. So I'll take natural log of 1/2, and that's equal to the natural log of e to the 5730K Natural log of a half I will keep as natural log of a half. Natural log of e to a power is always going to give you whatever the exponent is, whatever the power is, because the bases match. So 5730k. And then solving this, we're going to divide by 5730. You're going to divide by 5730. So we get k is approximately, I use 6 decimal places on this. You'll see why in a second. And I would say that probably get used to using 6 decimal places and then, reducing them later on. The more decimals you use, the more accurate you will be. So if I take natural log of 1 divided by 2, make sure you have that in parentheses, right? So natural log of a half divided by 5730. That gives us, I've got negative, right? It should be negative. Remember, these are decay examples, so it should be negative. 0.000, so there's 3 zeros there. 1, 2, and then that 9 will round that 0 up to 1. So 1, 2, 1. So k is approximately negative 0.000121. Make sure you know how to evaluate this on your calculator. It could be different depending on what your calculator looks like. Sometimes they'll write it in scientific notation. You'll need to know how to convert that back. So we found k. That's not what the question asks us to do, right? The question actually asks us to find how old is an artifact that's lost 60% of its carbon-14. But this k value we use back up here in our function for k. That's why we did it. So we're back to our function that was p of t equals p sub 0 e to the, now we know k is negative 0.000121 t. And now let's work on answering the question. The question says, how old is an artifact that has lost 60% of its carbon-14? Remember, my formula gives me how much remains. So if it tells you it's lost 60%, how much remains? Well, that means that, 40% remains. So watch your words here, right? So if you lost 60%, 40% remains, and that's important, right? So if you say 40% remains, that's how much we're looking for at the end. Now, I don't know how much I originally had, but I know 40% of it remains. So I can write this left side as 0.40, right? How old? This means we're still looking for time here. 0.40 of the amount that we had initially. So 0.40 P0 is 40% of the original amount. And that's how we're going to write the left side. It's equal to P sub 0. We don't know what that is, and it's okay. We don't need to know the initial amount. E to the negative 0.000121 t, right? Because we're looking for t here. So if it said how old is an artifact that has 60% remaining, you'd put 0.60 here. But since it lost 60%, you always go based on how much remains. That's what our exponential function tells us. And now we solve this like we have the others. To solve these, you always have to isolate the exponential first. So I'm going to divide by p sub 0 on each side. They cancel here, and they also cancel here. So you're left with 0.40 equals e to the negative 0.000121 t. And you can see this kind of follows the same type of format as we had for when we did it with half-life, or we did it with doubling time in the growth examples. In other words, it didn't matter what the initial amount was, those are going to cancel out when you go to solve this. So make sure you understand how this works. I would show this step. Sometimes people make an error here if they don't. Like they keep one of the p-zeros in but not the other. It makes the problem difficult to solve. Once I've done this, we're trying to get that t out of the exponent. The way we do that is by taking the natural log of each side, so we can use our log rule. So natural log of 0.40 is equal to the natural log of e to the negative 0.000121 t power. And then I'll leave this as natural log of 0.40 for now. It's equal to, remember, the natural log of e to a power is just going to give us the power of the exponent, because natural log is log base e of an exponential of log base e, or exponential e gives us the exponent. The bases match, in other words. So we got negative 0.000121 t. And then to solve this, we'll divide by negative 0.000121. Divide this by negative 0.000121. And we'll calculate that here. Natural log of 0.40 divided by negative 0.000121 gives us t is approximately, I've got here 7,572.65. This is, remember what we're finding, t is in years. So 7,572.65. This is years old. If you want to, because this number is so large, let's just round it to the nearest year. So T is approximately 7,573 years old. In other words, the artifact is approximately 7,573 years old. So, this example was a little different than the previous one because they didn't tell you the initial amount. Don't let that trip you up. Remember, when we're talking about the percentage of the initial amount, we're finding how much remains. So if they told you how much is lost, then how much remains is what you need on this side. So if you use, if there's 60% lost, 40% remains because it has to be 100 total. And then you can solve this. But the first step, if they gave you the half-life, is to find K from the very beginning, which is there's half the amount that remains of the original at that specific time that they gave you for the half-life. We'll look at one more example, and the text that we use includes this in the decay section, but really, they try to get you to use the same formula we've been using. I'm going to use it as kind of the growth formula, but we'll solve it for the part that it's asking us for. So it says a homeowner wants to have $15,000 available in 5 years to pay for renovations. If interest is compounded continuously is very important, at a rate of 6.1% per year, how much should he invest now to reach his goal? So first off, when you hear compounded continuously, you should automatically think that we're using our exponential growth formula. We got P of t equals P sub 0 e to the kt. All right, and we want to know that how much should he invest now. So when I say how much should he invest now, which part of this formula am I looking for? Well, I'm actually looking for the P sub 0, right? The P sub 0 is going to tell us, the initial amount. So I don't know that part, but that means I should know the rest of it. So $15,000 in 5 years, that means that he wants to have that amount be the P of t amount, right? The amount after 5 years. P of 5, in other words, should equal 15,000. And so we'll substitute that in. So P of t on this side is P of 5, which is going to be 15,000. It's equal to P sub 0, which is what we're going to solve for. We don't know what it is. That's what we're going to be looking for in this case. E to the, now what's K? Well, if we have 6.1% as our interest rate, remember how you use K, it has to be as a decimal. So moving that decimal place to the left too, we get 0.061, right? So K is going to be equal to 0.061. So 0.061. And then T, well, we know T, this $15,000 should be in 5 years. And we want to solve this, right? So we want to solve what we have here. So you're solving for P sub 0. So I end up with this. I have 15,000 equals, this is P sub 0 e to the, you might want to do this multiplication first just so you have it done. 0.061 times 5. I got 0.305. So e to the 0.305 power. And now how would I solve for P sub 0? Well, you would divide each side of this by e to the 0.305, right? Because this is P0 times this. So if you divide by it, it'll isolate it. So we got 15,000 divided by 0.305 is what P sub 0 should equal, because those cancel on that side. Well, that's the exact answer. But since we want to know this amount of money he should invest, we should calculate this. So you're taking 15,000 divided by e to the 0.305 power, and you end up with, I've got $11,056, and remember 2 decimal places for money, so 85 cents. So $11,056.85. This is money. This is how much he should invest at, so he will have $15,000 in 5 years. One of the key things to notice here is that we divided by this e to the 0.305. This is where, they tried to include this in the decay section, because they would have had you set this up with the 15,000 as your P0 and then have a negative rate on the K. would have gotten you to the same place, because e to the 0.305, if you were to rewrite this as e to the negative 0.305, you could write it in the same line with the 15,000. I find it easier just to use the formula we've always used, just like we did here. Use the k value that you have, use the t value they gave you, and then just solve for the p sub 0. So, this was just an extension of the last lesson on exponential growth. They both use the same formula. For growth, remember k is greater than 0. For decay, k is going to be less than 0. So hopefully these videos help and you're able to see the difference between the two types of problems you might have.